Okay, so now we're going to go over pressure drop, or major losses for laminar flow. While for practical applications, laminar flow isn't the most practical thing ever, but the advantage of laminar flow is we can solve the equations exactly and determine exactly what the pressure drop is. But we need some experimental results, and the analysis will actually show this. So experiments show that the pressure profile in a pipe, say that looks something like this, where there's an inlet, and we have the boundary layers, and this here's the entrance region. And this here's the fully developed region. Okay, and so there were some experiments done. You guys might do one of these in fluids lab, and x-axis pressure, and it turns out that the pressure will look something like this. Is that in the entrance region of the pipe it'll be nonlinear, but then after the entrance region it'll be a perfectly straight line in the fully developed region, and I'll just call this xfd, which of course you could calculate using the relation that I discussed in the previous lecture. Now the take-home point here is that the pressure gradient with respect to x is equal to a constant in the fully developed region. Okay, and so we are going to use that fact to our we're going to use this fact that the pressure gradient is constant in the fully developed region. So that is after the point where the boundary layers merge. That will make some of the analysis pretty easier. And so we're going to show this, that this is true just based on the characteristics of the flow. And then for laminar flow, which recall that laminar flow means that in the pipe, that the streamlines form nice little straight lines that don't tangle and cross and things like that. Okay, and for laminar flow, you can find the pressure gradient exactly. And you can do that in one of two ways. The first way, which I think is the easiest, is there are two ways. And the first way is to solve the Navier-Stokes equations. And this way is actually easier and more straightforward, but it is a little bit more, there is a bit of a learning curve to doing it. Kind of like when you do dynamics, you will learn Newtonian dynamics, or you've learned it, and then if you take an advanced dynamics course, you will sometimes go over Lagrangian dynamics, and when you do that, it will blow your mind how much easier it is to use Lagrangian dynamics in a lot of situations, even though it is more scientifically sophisticated. And when you solve the Navier-Stokes equations, you can do this exactly because we're going to assume steady, incompressible flow, all that stuff. Most of the nasty terms just simply drop out. Now, one thing that the Navier-Stokes equations one thing that you'll get out of the Navier-Stokes equations that you can't get from the way we're going to do it, but you can learn that U is a function of r and r only. Okay, so that is the velocity profile in the pipe, which we're assuming is circular, is a function of r and r only. It is not a function of angle. It is not a function of axial distance if it's fully developed. And furthermore, pressure is only and pressure is only a function of x. It is not a function of r. And so if you work with the Navier-Stokes equations, you learn that information directly. Okay, and so at this axial station here, anywhere on this velocity profile, the pressure is constant. Okay, so we'll just keep those in mind. And now the second way to compute dp dx is to just consider a differential stress element. Okay, so here we're just going to consider a circular tube. Oops, got to shrink the screen. A circular tube. And this here is the center line. R and the radius and the outer wall of the tube is at radius of capital R. Okay. So here we're going to do a differential control volume, and I'm going to draw it in kind of a funny way, because this differential control volume is actually in annulus. So if I look at a cross section of the tube, it looks like a big old circle, and our control volume just looks like a differential ring. Okay, and so we're going to analyze the stresses on this differential ring. And so this would be the top of the annulus, and this would be the bottom. Okay, and so we're going to consider momentum. And like we did for the Navier-Stokes, or like you did for some of the homework problems, we're going to use the integral form of momentum on a very, very tiny differential control volume that is ring-shaped, like you see here. And we're going to assume steady flow, and we're going to assume incompressible flow. So we have partial time acting on the volume integral of rho v dv plus the surface integral of the net momentum flux out, so that's v rho v dot n hat dA equals minus the surface integral of p n hat dA plus the sum of the viscous forces acting on the control surface plus the sum of the body forces. Okay, we're going to neglect the body forces. We're going to assume steady flow. And we're going to, and since we're including viscous effects, we must include the viscous stresses. We have to include pressure. And now this term here, we are assuming fully developed flow. So this term actually goes away. So if it's fully developed flow, that term goes away. And also, I'm going to scroll back. I'll scroll back up again. And one thing we also learned from Navier-Stokes equations is that V and W equal 0. So that is the only component of the velocity is along the tube itself. There is no component of the velocity that is going up towards the wall or around in circles. It is just going straight along the tube, only in that direction. Okay, so if it's fully developed, let's just draw a little control volume here, and I'll prove this result here. So we just draw a little control volume, and it doesn't need to be differential. But we're assuming that rho is constant, and so we have v, rho v dot n hat times an area that is going out on this face times an area, and we have rho v dot n hat times the area. Well, n hat is pointing in the minus I hat direction here, and over here it's pointing in the positive I hat direction. And since I know that v hat equals ui hat, because you can prove through Navier-Stokes equations that the velocity is only going in the x direction, that means there is nothing in terms of the velocity that is going up through the top or down through the bottom. Okay? And furthermore, because it is fully developed, the velocity at this point here, which is further downstream, is equal to the velocity at this point here. So v on left equals v on the right. Okay, and I'll just call that v, like I have there. And rho is constant. Okay, and v dot n hat on the left equals minus v dot n hat on the right. Right, and that's just because you have the same v, oops, wrong one. You have the same v on the left and the right, but the I hats are in opposite directions. Okay, so this implies that v, rho v dot n hat times area on the left equals, or I should say minus plus integral of rho v dot n hat times area on the right equals 0. Okay, and that's because the areas are the same, oops, times the area, got to squeeze that in there. That's because the areas are the same on either of these faces. V is the same, rho is the same, and v dot n hat, the magnitude of that is the same, and I've taken the sign into account here. So these basically just cancel out, and this equals the surface integral v, rho v dot n hat dA. So basically that term cancels out because the velocity a is going only in the x direction, and because it's fully developed, that means the velocity at this axial position is the same as the velocity at this axial position. So essentially then, momentum equation just turns into a nice stress balance. And so we don't need to account for anything else. So we just consider a free body diagram. So only pressure and viscous stress survive. Okay, so let's draw, and so basically what this means, what momentum is now telling us, is that this fluid element here, or this control volume, it's in static equilibrium. These terms here represent the time rate change of momentum, which is the acceleration, and so there's no acceleration, and if there's no acceleration, that means your object is in static equilibrium. And so we just do a static equilibrium analysis on this, and that's exactly what momentum told us to do. So now I'll draw a more formal differential cube. And so now remember, this is an annulus, so I'm just drawing the top part of it, and that's R. This is the center line down here. And so on this side, oops, wrong one. On this side, I'll have pressure pushing to the left, And so that'll be P at x plus delta x over 2. And the area over here, that's the area of an annulus. So I'll just draw that over here. A equals 2 pi r delta r. Okay. And because that's just the area of this annular face here. Okay. And over here we have pressure pushing to the left. So that's P at x minus delta x over 2. And the area here equals 2 pi r delta r. Okay, now we have viscous stress, and there is no gradient. There is no vertical velocity component here, so there's actually no shear stress going in the top and bottom direction. And again, you have to go to Navier-Stokes to prove those kinds of things. So the only stresses that survive are the shear stresses on the top of the face going in the x direction. And so that's tau Rx at r plus delta r over 2. And we have a shear stress on the bottom, and that's tau Rx at r minus delta r over 2. Okay, and now on the top and bottom, we do need to be careful with the area. So the area here equals, and the width of this cube is delta x. And the height is delta r. I should have said that earlier. Sorry about that. Okay, and the center is at location r. So the area is just the area of the top part of this ring here, and so that is the width, which is delta x, times 2 pi times the outer radius, and that is r plus delta r over 2. Okay, and so that's just the area of a ring. Okay, and then we got the bottom. The area here is equal to delta x times 2 pi times the radius at this position here, and that's r minus delta r over 2. Okay, and so now we just sum the forces in the x direction. So the sum of F equals 0 in the x direction, and I'm not going to prove it, but there are no y forces, and so we just sum the forces in the x direction, and so we have pressure times the area at x minus delta x over 2, and so we've taken care of this, minus pressure times area at x plus delta x over 2, so we've taken care of this, plus the shear stress acting on the top here times its area, tau Rx times area at r plus delta r over 2, minus the shear stress acting on the bottom. So that's tau Rx times the area at r minus delta r over 2. And this is equal to 0. Okay, and this area here, or these areas here, are equal to 2 pi r delta r. This area equals 2 pi r, not 2 pi r, 2 pi delta x times r plus delta r over 2. And this area here is equal to 2 pi delta x times r minus delta r over 2. Okay, and so all I've done was I've just taken care of the pressure forces and the shear stresses. Okay, and we don't need to consider the y direction because the result from the Navier-Stokes equation says that the pressure pushing up from the bottom is the same as the pressure pushing down from the top, so there are simply no y forces. There are no net y forces acting on this control volume, on this free body diagram that can give us any useful information at all. Okay, So I'm going to put everything together and start working with this a little bit. So this starts exploding into a bit of a mess. So substituting the areas. We have 2 pi r delta r times pressure at x minus delta x over 2 minus pressure at x plus delta x over 2. Okay. And again, using Taylor series, that f at x plus minus delta x over 2 equals f plus minus delta x over 2 partial f partial x. Okay, and again, we're doing a differential control volume, so there's no need to do the plus delta x squared over 2 times 2 factorial partial squared f partial x squared. There's no need to do any of the higher order terms here, because they would all cancel out anyways. Okay, and so as usual, if you did the Taylor series, you've probably seen me do it enough and you've done it yourself, probably more than you wanted. This term turns into minus delta x partial p partial x. Okay, and it's minus because normally we had the plus delta x on the left and the minus delta x on the right. Okay, and so that takes care of the pressure forces. Now we got the viscous stresses. And so we plus 2 pi delta x times r plus delta r over 2 times tau at r tau rx at r plus delta r over 2 minus 2 pi delta x times r minus delta r over 2 tau rx at r minus delta r over 2. And so here we have these extra terms. Here, this plus delta r over 2 here, and this minus delta r over 2 here. So we can't do the nice simplification that we did, that we've been doing till now. But nonetheless, so I'll just directly substitute the Taylor series as tau rx plus delta r over 2 partial tau rx partial r. And this term becomes tau rx minus delta r over 2 partial tau rx partial x. Partial r. Okay, and so we substitute that in. Then we have 2 pi r delta r times negative delta x partial p partial x plus, this is going to explode into a bit of a mess, 2 pi times r plus delta r over 2 delta x times tau rx plus delta r over 2 partial tau rx partial r plus, and I'm going to put negative here, 2 pi r minus delta r over 2 delta x times tau rx minus delta r over 2 partial tau rx partial r. Okay, and so I'm just going to simply expand these terms here and then simplify. And so simplifying, and that's just really algebra at this point. If you do the oops, and I forgot, we have an equilibrium condition here. So we wind up with 0 is equal to partial p partial x, and again I'm skipping quite a few steps, minus partial tau rx partial r plus 1 over r partial tau r. Oops, that's not partial, that's just tau rx. Okay, and that's not plus, that's minus. Okay, and so essentially how we get to that is we just expand these terms out here, and most of them cancel out, and you divide by 2 pi r delta x. And when you do that, you wind up with these terms here. And now there's a nice simplification that we can do here. And if we notice that, note that df some function dr plus f over r, that equals the quantity 1 over r times drf dr. Okay, and this is probably not obvious to a lot of you, but you can check with the product rule. So when you are working with these systems, this perfect derivative here is much easier to work with the two derivatives separated, because as you could imagine, we're going to wind up solving an ODE, and an ODE involving this is a lot easier to solve than an ODE involving these two terms here. Okay, and so using this result, that these two terms here then become minus 1 over r partial r tau rx partial r. Okay, then we have partial p partial x equals 1 over r partial r tau rx partial r. Okay, and now we need to know what tau rx is. Well, from tau rx equals mu times partial v in the radial direction partial x plus partial u partial r. Okay, and u here is the axial component. And this is the radial component. And from Navier-Stokes equations, we know that VR is equal to 0, but also because it's fully developed, we can also cross this term out because none of the flow velocity is a function of x. And so the derivative of any velocity component with respect to x is 0. So then this term cancels out, and we wind up with that tau rx for our pipe flow is equal to mu partial u partial r. And u is only a function of r. And again, you need to look at Navier-Stokes to prove that. But u is only a function of r because it's fully developed, because it's steady, and all that good stuff. And so if tau is a function of mu, which we're going to assume constant, okay, so we're going to assume that mu is constant. So mu is constant, and this is a function of r only. That means that tau is a function of r only. And so that means this whole term here is a function of only r. So that's a function of r. And also, we argued that pressure is a function of x only. So over here we have a function of x. And we have a function of x over here equal to a function of r over here. And there is only one way that you can have a function of one variable equal to a function of another variable. So we have f of x, some function of x is equal to some function of r, and there's only one way to have a function of x equal to a function of r, and that's only possible if both functions are equal to the same constant. Okay, thus partial p partial x equals 1 over r partial r tau rx partial r equals a constant. Okay, so furthermore, we have proved, at least for laminar flow, that partial p partial x is constant in the fully developed region. So this means that the pressure gradient that the pressure profile forms a nice straight line in the fully developed region. Okay, and that's basically all that means. Okay, and so now we solve this, and so now we're going to take it a step further, because to evaluate dp dx and pressure as a function of x, we actually need to integrate these equations here. And since dp dx is equal to a constant, I'm just going to call this thing q. And I'm just going to call it q because I'm lazy and I don't want to write dp dx 500,000 times. Okay? And it's equal to a constant. And so we're going to solve, and tau rx equals mu du dr. Okay? And so that was what we learned from the stress. And so we have q equals d dr. Again, tau is a function of r only, so I can change these partials here to just normal derivatives here. d dr of r tau rx, 1 over r. Okay, that implies that d dr of r tau rx equals r times q, just multiplying both sides, where again q is just dp dx, which is a constant. Well, this is a separable ODE. And doing that fancy trick with those two stress terms to turn it into this perfect derivative turns this into a very easy to solve separable ODE, where you just integrate both sides. And so this implies, that d r tau rx equals rq dr, and we just integrate both sides. We have, this is a perfect derivative, so we just integrate that. So that's r tau rx equals 1 over 2 r squared plus some constant c1. Okay. Or tau rx equals 1 over 2r plus c1 over r. Okay, and now here we can actually apply a bit of thought to this, and that our pipe looks something like this, and here's the center line r, and the outer radius is capital R. So this is saying that the shear stress is equal to a linear function of r plus some constant divided by r. Well, at r equal to 0, which is right here, is the center line of the channel. And we care about the center line of the channel. our ODE is being solved to the center line of the channel, so R can be 0. And our equation must be valid where R is 0. So basically, C1 equals 0 C1 equals 0, and this must be the case. Or tau Rx will approach infinity as R approaches 0. Okay? And an infinite shear stress at the center line of the channel, or of the pipe, makes no physical sense whatsoever. So it must be bounded, and the only way for that to happen is if the integration constant is in fact 0. Okay? Now, it looks like we're sort of done here, but we aren't. Tau is equal to the viscosity times du dr. So we substitute that in. So we have mu du dr equals 1 over 2 r. Okay. Then we then integrate, and we assume constant viscosity, and so we have mu du equals 1 over 2r dr. And so we integrate this, and we have mu times the velocity is equal to 1 over 4 r squared plus some constant c2. Okay? Or u, which is a function of r, is equal to 1 over 4 times the viscosity, r squared plus c2 over mu. Okay, and so now we need to find C2. And how we find C2 is we recall the no-slip condition. So here's the center line of the channel, R and capital R. And so at the very surface of the channel here, U is equal to 0 by the no-slip condition. Okay, and really what the no-slip condition means is that the fluid velocity at the wall is equal to the velocity of the wall, which is 0. It's just a stationary pipe, and that's even born in the profiles that I've been drawing, is that the velocity profile is maximum at the center line and 0 at the walls of the pipe. And so we apply that. So this implies that U at the outer radius is equal to 0 by no slip. Okay, so U of R equals 0 equals 1 over 4 mu times capital R squared plus C2 over mu. And we can solve for C2 equals minus 1 over 4 R squared. Oops, I missed a Q here somewhere. Sorry, I missed a Q. Q times Q, and that'll be Q. R squared Q. Sorry, all the R's above should have been multiplied by Q. Sorry about that. So then finally, U of R equals 1 over 4 Q over mu times R squared minus cap R squared. Where again, remember that Q is just the pressure gradient, dP dx, and I'm going to do some simplifying. U of r equals minus cap r squared times 4, or divided by 4 mu, times dP dx times 1 minus r over cap r squared. Okay, so way back earlier in the class, you remember us. When we were working with conservation of mass for the first time. You remember me doing examples and giving homework problems where you had to integrate this profile right here in a channel, and that's actually where that profile came from. Is that the velocity profile is parabolic. Okay, and so the velocity profile looks almost like I've been drawing all along, is that it's just a perfect little parabola. And the note that if we look at this negative sign here and the dP dx, is that the u, or the axial velocity, is in the opposite direction as dP dx. Okay, and so that means if the pressure gradient looks like this, then the flow velocity is going in that direction here, and that makes sense because that means you have more force over here that is pushing the fluid that is pushing the fluid to the right. Okay, and so intuitively you would expect the flow to go from the region of high pressure to low pressure. Okay. Okay, and I will end this lecture here, and we will start working with this profile a little bit.